In addition to the hydrogen spectrum, Bohr needed to address the planetary orbits of the electrons. The Rutherford model had electrons held in place by the Coulomb force, which kept them in a circular orbit, hence providing the centripetal force. So the centripetal force was between the electrons and the positively charged nucleus. That was fine. But as shown earlier in the 19th century by Maxwell, an accelerating charge would emit electromagnetic radiation. And since the electrons were constantly accelerating, and again in this model it's a centripetal acceleration, they're going around in a circle, that is acceleration even if they keep the same speed, they would lose energy. This loss of energy would cause the electrons to slow down, and if they weren't going fast enough, they would fall out of orbit and collapse onto the nucleus within 10 to the minus 11th seconds. That of course doesn't happen, as evidenced by the fact that we're all still here. So here's the Bohr atom. We have an electron right over here. It's being held in orbit by the Coulomb force, where here's your nucleus, and let's say there's Z, atomic number Z, so it has a positive charge of Ze. You have a distance here, the radius of this electron's orbit, so you use Coulomb's law, which is K, Coulomb's constant, times one charge, this is the nucleus right here, Ze, the charge on the electron, and you divide that by the distance squared. Niels Bohr had to make the following two assumptions to address the shortcomings of the Rutherford model. It's called a semi-classical model, as Bohr is combining classical physics with aspects of the emerging quantum physics. Bohr stated, electrons could only revolve around the nucleus in specific circular orbits, not just any circular orbit. They had to have a fixed angular momentum and energy. The further away from the nucleus, the greater momentum and the greater energy. Now here's the amazing statement he made, just to make it work. Frankly, there's no experimental evidence for this. It was just part of his theory. If the electrons were in these orbits, the electrons would not radiate electromagnetic energy. Again, there's no reason to say that other than it makes the model work. Now, energy will be emitted from the atom, and the energy takes the form of light when the electrons jump between these orbits. Now, because they're in very specific orbits, there will not be a continuous spectrum of energy. The energy is quantized. So here you can see the semi-classical nature of this. The notion of quantized energy is clearly quantum mechanics. It is not classical. So only photons of a particular energy is emitted. This would represent the energy difference between the allowed orbits. Here's what it looks like. This is a model of electron orbits. Right over here, this is the nucleus. Here's the first allowed orbital, n equals 1. You can see the circle here that an electron can be in. Then n equals 2, a little further out. N equals 3, further out still. And the energy increases the further you get away from the nucleus. So what we have here on the bottom, hope you can see this, the electron is moving from orbit 2 to orbit 1. It's losing energy. It's going from a higher energy level to a lower energy level. When it does that, that energy has to go somewhere. So it gets emitted as a photon. Photons are typically drawn with the wavy line. And the energy is quantized. The energy is E equals h times the frequency. Let's take a quick tour through Bohr's mathematics. Bohr made the assumption that the angular momentum, which is r times p, or mv times r, for each orbit had to be quantized. It had to be an integral multiple, n, where n is 1, 2, 3, etc., times Planck's constant divided by 2 pi. Where did he get this? He made an assumption, and then the math worked out. It's just amazing feat here. Now let's look at the Coulomb attractive force. Between the nucleus of charge Ze and the single electron, remember, that's the force, and the sum of the forces, according to Newton's second law, is m times a. In this case, since it's a centripetal force, we have centripetal acceleration, so the force will equal mv squared over r. So here we have the force. Here's again, this right here is the nuclear charge. Here's the electron. Here's the radius of the orbit, and it's r sub n, again, where n can vary from 1, 2, 3, etc. Do the multiplication, and we set this equal to mv squared, again over this Rn character. This is the radius of the nth level. On this page we're going to wave our hands a little bit, and if you'd like to do the math, this is well within algebraic skills and the physics you've learned already. We'll combine the two equations from the previous page and we'll solve for the radius of each quantum level. And notice that the radius depends on the atomic number of the nucleus Z and also the atomic orbital number 1, 2, 3, etc. And it's n squared, Planck's constant squared, 4 pi squared, m k z e squared. We'll use some more equations. Again, classical equations. Bohr's solution is semi-classical, but it's solidly rooted in classic mechanics and E and M. So we have Coulomb's law, Newton's second law, angular momentum definition, potential energy, kinetic energy, and Bohr's quantum assumption. And we can calculate the energy of the various quantum levels. Again, this is for hydrogen-like atoms. These are atoms that only have one electron. And we come up with -1/8 mz squared e to the 4th epsilon 0 squared n squared h squared. And it's negative. This negative is a very important thing. That shows that it's a bound state. These electrons are bound to the nucleus. Let's simplify all the letters in the equation from, again, the previous slide. We're going to define the Bohr radius. The Bohr radius, a sub 0, that will be defined as the electron orbital radius for the ground state. Ground state is n equals 1 of the hydrogen atom, which you'll recall hydrogen is the first atom in the periodic table, so Z equals 1. We substitute in all the constants and those two values, and we find that the Bohr radius is 5.29 times 10 to the minus 11th meters. We can then express the radii of other hydrogen-like atoms as just the Bohr radius right here, A0, times n squared, which is the quantum orbit level, divided by Z, which is the atomic number of the other hydrogen-like atoms. And you can notice from this equation that as you get further out, as you have n equal 2, 3, etc., the orbits grow in size as the square of n. So they get much, much larger as n increases. Now let's look at a numerical value for the energy levels. We take the energy equation, we put in the constant values, and we come up with the energy of any electron orbital is going to be minus 13.6 eV, where the minus sign means it's a bound state. It's not leaving, the electron's staying attached to the nucleus, times Z squared over n squared. What's interesting here is the further out the orbitals get, the energy levels actually get closer together, and they get closer to 0 as n increases. So what you have here is, here's your n equal 1 level. You'll have n equal 2 somewhere like this, then n equal 3 a little closer, n equal 4 closer still, and that's how they progress in terms of increasing energy.